to a journey through multiple scales in space and time. We will explore a little bit how different batteries can be modeled with COMSOL today. My agenda, in the introduction, I want to answer the important question, why modeling batteries? Isn't it enough when we measure them? Then I will especially talk about lithium-ion batteries in different scales, compare high fidelity with some simplified approaches, and show you also through a couple of regular analyses like load cycle analysis, impedance spectroscopy, thermal management, and others. And I have embedded a couple of live demos in my presentation today, so you don't have to wait for 40 minutes till I open COMSOL for the first time. I will do that rather quickly. And I'm very open to questions afterwards. So if you want to post something in the chat, we will hopefully find that as well. So let us turn to the first point, why model batteries? Well, for me, the answer is quite simple. Modeling is a very time-efficient way of improving our understanding of the processes that happen in batteries. If you are an experimentalist, work a lot in the lab, like the nice lab that I have seen recently in Biel with the many thermal chambers where you can expose batteries to all sorts of conditions and test them in all environments. Then if you are an experimentalist, you probably believe in your measurements, but most experimentalists probably agree that not all properties of batteries are really accessible to direct measurements, and at least not to non-destructive ones. And also the design of batteries is often driven by trial and error, which can be quite time consuming. And we believe that simulation can add here some extra knowledge. Simulation works with equations, works with abstractions and assumptions. For some people, this means that we are lacking the street credibility a bit that an immediate measurement has, because it's just what you get when you when you measure. However, careful modeling based on good validations and experiments allow us to calibrate our models to get surprisingly accurate predictions. And the good thing is, once you have such a model, you can apply it to all sorts of scenarios, different load conditions, different temperatures, different geometries, and you can create a multitude of simulations and harvest a lot of knowledge. In the end, we want to help industry to manufacture better batteries and optimize for this device manufacturers. We hope they can use simulations to optimize the load cycles, for instance. Who can benefit from simulations of batteries? We believe that all stakeholders throughout the whole battery value chain can benefit. Maybe the first and early most adopters were academic researchers, but today battery manufacturers can optimize their designs. People at test facilities interact with models to extract or inversely calculate characteristic properties from their measurements. Device manufacturers can optimize, as I already mentioned, their load cycles. And finally, lifecycle managers can even create a full digital twin of their battery system if they want. And on the right-hand side, you see this image that we have in mind, people on all levels of planning, research, design engineers, process engineers, and even field technicians and operators can benefit from simulations. How that goes, what we have in mind and in stock for you, this will be the topic of my talk. COMSOL is a general purpose simulation tool for all kinds of physical processes, including structural, thermal, electromagnetic, chemical, acoustic, and others. And especially we have a suite of products for electrochemical processes, electroplating, corrosion, general electrochemistry, fuel cells and electrolyzers, and this battery design module that I want to introduce to you today. It excels by ease of use. It has tailored functionality for current distributions, for certain battery types, for porous electrodes, for dilute and concentrated electrolytes. And it offers you a lot of coupling to other fields, like what you see in this picture, an external airflow, for instance, or structural deformations, mechanical swelling, and other topics. Which batteries can we model? So the ones that we target, especially, of course, the most important one or most popular ones at the moment, lithium-ion batteries, but also lithium air, lithium sulfur, nickel metal hydride, solid-state lithium ion, lead acid, nickel cadmium, zinc silver, and others. Also flow batteries are possible, and yeah, we are constantly extending the functionality in that field. Now, how does it work? In COMSOL, you would start in drawing or creating your geometry and then selecting equations from a drop-down level. Here, for instance, you see we have some general electrochemistry interfaces like primary, secondary, and tertiary current distributions. But the main talk today, or the main purpose of my talk, is to introduce you to those interfaces, especially lithium-ion batteries and others, lumped batteries, single particle batteries, and equivalent circuits. We also have interfaces for general chemical species transport, fluid flow, single phase, porous media flow, and heat transfer in fluids, solids, and porous media. Now, COMSOL also comes with a library of battery materials. You can see on the right side what you get when you press the button Add Material. You see a number of anode and cathode materials and electrolytes. And if you click on one of them, then you would get a whole list of material properties, for instance, electrolyte conductivities, equilibrium potentials, entropic heating, diffusion coefficients, transport numbers, densities, heat capacity, and others. And these properties can be constants, but they also can be functions. They can refer to table data and other things. Why not actually opening COMSOL at that point and guide you through the first steps? So in COMSOL, you would create a new model. First of all, select the space dimension in which you would like to work. Well, let's take for the moment just a 2D model. And then you would select from the electrochemistry department here, as you can say, the batteries, and then, for instance, lithium-ion battery chemistry. Yeah, we add this to our model, and we see the equations will be solved for the potential salt concentrations. Yeah.
Are you showing now the tool? We don't
yes,
see
can you?
Yeah, no.
You don't see it?
No, we just
okay,
see
good. Then probably need to share the screen. This should be this one then. Can you see it now?
No.
Now?
Yes, now I see. Yeah, that looks good.
Okay, good. Very good. Yeah, I just switched to the background here. So lithium-ion battery, we could select different types of studies, for instance, time-dependent or stationary studies, or also electrical impedance spectroscopy. So After that, you would then go first into the geometry department. We typically work in the microscale here. So let me switch to micrometers. And then you would start, for instance, drawing a rectangle, let's say of 100 microns across. And what shall we take? 325 in height. We can add layers for the electrode material and the separator, so that we can at least get 3 layers, and then you would start assigning materials, selecting from the material library, from the battery department again, electrodes, for instance, graphite electrode, and then we also need an electrolyte, for instance, and just mention this here briefly to show you what kind of material data would then be available. We see this in full beauty later on. Here you see, for instance, diffusion coefficients and other things for the graphite electrode. We have a couple of more things available here also as functions of temperature. Now, regarding study types, let me switch back to, I think I should be now back to, can you see my presentation again?
Yes.
Okay, good, excellent. So regarding study types, stationary studies for batteries are rare. Most commonly, you have transient loads or transient behavior, at least, with dynamic load curves. And some studies work with frequency domain analysis, namely the electrochemical impedance spectroscopy that I will mention later on. Now, solving equations efficiently alone is not enough to be a leader in industry simulation software. We have to have a couple of soft skills, for instance, built-in optimization, parameter estimation to fit model parameters to your experimental data. We have released in the latest version COMSOL 6 a so-called uncertainty analysis or uncertainty quantification module. We offer you the ability to import CAD files from various formats and even live links to certain well-known software products. Extended physics means we can couple the battery design module with all other functionalities that COMSOL Multiphysics offers, including interfaces to programming languages, but also, of course, all the physics that I have already mentioned, structural, CFD, and others. Now, one of the most fascinating developments of the last years is our ability to turn every simulation into a application, into a piece of software that runs on an independent computer, royalty-free, royalty-free, standalone, or you can access this through a web browser and make it available to the large audience of people who could potentially not write a battery model, but definitely benefit from it and operate it. And this is something I want to definitely show you, just to introduce you to the overall idea that we have in mind here. So you see my console again? I'm asking because we had a problem before.
Yes.
Okay, so I'm going now to the library of tutorial models that we have, and there is the lithium battery pack designer, and I want to show you what I mean with application level. Yeah. First of all, you will see now, if we switch to the model builder, that's basically the engineering interface where the designer of the model, the simulation engineer sets up the thermal and electrical properties of the model, and he defines a certain number of studies and things in here. This is the level that I have shown before. And it can be quite complex for someone to build this up. You see, there are a couple of settings that need to be done. But if you switch to the application builder, you can actually see what a non-specialist could operate with. And it appears now on another screen. Here it is. So here we only have basically an interface where we have a table with entry possibilities. We have a help system. We can easily operate that, for instance, switch to a simple battery system, 1x3 batteries. We can update the design and look if it's the one that we want. Maybe I wanted rather 3x1. It looks slightly different. Okay, something like that. Yeah, okay. And then you see I can also change the dimensions of the battery. I can change the thermal properties if I want the external temperature, or I go to the battery cell level and change some electrochemical data. And in the end, I just press compute, and in a couple of seconds, I would get a thermal analysis of this 3x1 battery system under a specific load. I have not shown that you can, of course, import a load curve and see how it behaves. So this is a completely different level of approach. Someone operating this doesn't have to set up anything low level. They can just work with interfaces and enter some data and extract what they want to extract. We can animate that easily to see the temporal evolution of the battery temperature. And yeah, so that is the level of applications, and you can publish it, you can sell it, you can make it available on the web to others, or give it away for free to your students if you want. So I hope you find that exciting. Now let us look a little bit closer under the hood of our capabilities, slightly more theoretical or slightly more engineering style now for the next couple of minutes. Let us start with a very common typical schematic representation of a lithium-ion battery, where we have two current collectors made of copper and aluminum with an anode material, typically graphite or lithium titanium oxide or others. Then we have the electrode separator, and we have the cathode on the right side. The whole system here would be in the sub-millimeter scale. We have a 0.5 millimeter maybe across that cell, and we can now connect our system to a load. And as we all know, we have an oxidation happening at the anode side, producing electrons that flow through the load and eventually recombine with the lithium ions that go the other way, namely from the anode inside the battery through the cathode, where the lithium ions are reduced to form the porous material, again, or lithium cobalt oxide. And yes, this is a very well-known model, and it helps us to understand what's going on. We know that the stability of the lithium ions in the cathode is much higher than in the anode, and that's why we can harvest energy from that system. And luckily, the process is reversible, so we can recharge our battery later on. Now, this approach or this picture of a battery works well to understand certain things, but it is has also its limitations. Yeah. The cell scale models operate in dimensions of few hundred micrometers, as I mentioned, but in the batteries, also other length scales are important. You can see here the pore scale model, for instance. This is a heterogeneous model where each of the grains is displayed, and we see how the lithium penetrates the grains, and we can have surface reactions, we can have volume reactions, we have a flow through the pore space. So this happens at the scale of maybe 10 microns. But then the cell is usually spread out and connected to other cells to form a stack, or to be spirally wound as a jelly roll. And then we form eventually a system that can be a couple of decimeters big or even in a meter scale. And if we were now to model a meter-sized object with a grain distribution of 10 microns, we would sooner or later approach a limit of computational feasibility. So that's you need a very powerful computer to do that, and it wouldn't be fast, I can tell you that. So every length scale has certain benefits if you want to explore certain features of batteries. The heterogeneous model, as I mentioned, is the most precise. It models the electronic conduction, the electrolyte ion transport, solid lithium transport by diffusion into the grains, or also the heterogeneous electrode reactions. This geometry, this nice geometry, by the way, it's based on a paper by someone you might know, Martin Ebner from Switzerland, and the group of Vanessa Wood at ETH. They have published a paper where they made available this pore scale geometry, which is today used for a tutorial of COMSOL as well. And you can either import images to create that pore space model, or you can also create it by randomly placing little spheres in a cube, for instance. That's also possible. Now, why is it necessary to homogenize? I already mentioned it's about computational efficiency. A model like the one that we have just seen, a couple of 100 micrometers big, heterogeneous, would take a few minutes on a desktop computer for a simple single discharge or charge operation. But we want shorter computation times because we want to go for thousands, hundreds of thousands of charge-discharge cycles. We want to go for geometric parametrizations, maybe for something like machine learning and other things. So we need to create many models, and they shouldn't take several minutes. This homogenization approach actually already appeared in the 1990s, and it was published by Doyle, Fuller, and Newman, and it's well known as the so-called Newman model. And the Newman model makes a certain abstraction. It is homogenized, as I already mentioned. It no longer contains any grains, but we use homogeneous materials. But we assume that at every space point, x and y in this model, we are solving additional diffusion equation inside the grain in a so-called extra dimension. Extra dimension, big name, sounds a little bit like extraterrestrial. It's not complicated to understand. Imagine you have a two-dimensional coordinate system, and at each point you have an additional coordinate system with one coordinate representing the radius, and you can simulate the diffusion into the spherical particle. And such a model like here, it would be called 2D plus 1D, making a P3D model. You can also have it in 3-dimension, a so-called 3D plus 1D, or also 1D plus 1 extra dimension would be P2D model. And apart from that, we also offer other simplified battery modeling interfaces that cannot reproduce all the features of a battery, but are very fast solving, like the single particle battery. This would assume that in the Newman model, you don't have any spatial variation of concentrations anymore, and also the electrolyte is completely homogeneous. And then you can say this all happens in a single particle, which is very computationally efficient. And The lumped battery model is even one step further. It integrates both electrodes into one particle. It's a particle approach. It has a very low computational load and can be easily coupled with heat transfer simulations. The probably coarsest level of models that we can offer are equivalent circuits. Here we would assume that the battery can be represented by a system of capacitors and resistors in a circuit. Yeah, and when we take one level of abstraction, one step forward, and go to a coarser model, we want to make sure that we don't lose important information. Yeah, and that's why we compare our models of different scales. Here in this picture, you see, for instance, a high fidelity model. In this case, it is a Newman model for a certain battery discharge and then recharge cycle. And the other model is the single particle model. And you see it basically follows the same characteristics, but it also has some deviations. We need to explore what we lose or what we gain when we switch to another level of abstraction. All models will be similar, but some will be more meaningful under certain conditions. For instance, the lumped battery model is applicable if you have low to moderate charging rates. You could not really apply that to extreme charging rates of tenths of C, for instance. Then it's not accurate anymore, and it's known, and you can even model both scenarios and find the differences. Now, let me summarize what we can offer in terms of battery model interfaces. We have heterogeneous models, modeling the full grain size geometry and all reactions in their full beauty. We have homogenized Newman approaches. We have single particle and lumped approaches, and we even have equivalent circuits. The benefits of the heterogeneous models or of the complicated high fidelity models are they are accurate, they cover a wide range of validity. They are, on the other hand, very expensive to compute, and they require also more inputs from you, knowledge about electrochemical parameters, about electrode geometry. And by contrast, the more approximate models, they would be much faster, but typically have a limited range of validity, but they would also need fewer inputs from you. So they are typically easier to operate if you are still in the early phase of your battery project. When you don't have complete knowledge, you just want to test something quickly, then the approximate models are ideal. So let me cover a couple of typical analyses. What can we do? Most commonly are time-dependent simulations of batteries in load cycles. We can have a constant discharge rate, for instance. Then this upper graph here would show us what happens at slow discharge, and if we slightly increase the rate from 0.1 C to 1, 2, or 4 C, we get much faster decay of the battery voltage. Now, the charge doesn't need to be constant. We can, of course, have certain cycles of the load. As you can see here in the lower diagram, we have a certain time of discharge, then we have a certain recovery period, then a recharge, and then a relaxation again. And we can extract from those models the behavior of the state of charge and the cell voltage. At that point, I want to quickly open a battery model again. I take it from the application library, and it is called the Lithium Battery Designer. When I open it, you will see that it is actually this time a one-dimensional model. You see, I have only a line with 3-4 points on it, separating the anode, the separator, and the cathode. We do not need to model at that stage the metallic current collectors. It is essential here only to model the electrochemistry. We're using the one-dimensional lithium-ion battery interface again. We define the porous electrode, the negative electrode, the positive electrode, and the separator. There are some settings, but most of the properties are inherited from material. And as you know already, we have set here, for instance, the LPF6 material that would bring us the diffusion coefficient in the liquid, in the electrolytic medium, transport numbers, activity dependence, and things like that. What else do we have here except of the lithium-ion battery? We have events. Events are, as it's understood, discrete events in time where we want to make sure that something happens, like switching from loading to relaxation to recharge. Yes, and then these events also will trigger the solver to have small time steps at the moments where something happens, so that they are very accurate in the vicinity of heaviside jumps in the load. Let us check what the end user could see in such an application. It's again, someone has taken the time to build a little user interface around. We first can select the canister type, the cell. The collector thickness is not drawn, but it influences still the behavior, the thermal behavior of the battery, because it has a certain thermal delay. Then a thermal inertia, positive electrode. Here we could select different materials easily, change the radius of the particles, the active material volume fraction, and other things. And we could define also the load cycle, how long, how many seconds, or if you want to switch to C rates, we can say we want to have a charge of 1C and a discharge of 2C and things like that. Okay, but in the end, we can press the compute button, and after a couple of seconds, again, we would see the temporal behavior of a number of battery properties. Yeah. Again, this app appeals to people who don't want to set up something from scratch, but already use a predefined interface to quickly check a couple of assumptions or visualize the behavior of certain things. Yeah. So we can, for instance, check the positive or the negative electrode potential. We can check the parasitic losses if we want. And we also can look into profile plots across the electrodes. We see this is 230 micron thick, and we could identify also the different electrode separators here, for instance, because we have a little, a corner in our curves. And again, without going deeper in this model, just wanted to show you how easy it is to model load cycles. Now, what else can you do with the battery design module? You could do parameter fitting. For instance, if you have a rough idea about your battery, but you're lacking a couple of properties, but you have measured extensive time series, for instance, of the experimental cell voltage during a load cycle and the open circuit voltage, then you can have the program estimating the missing parameters like the ohmic overpotential, the charge exchange current, or the diffusion time constant. And you see here the fit after the computation is done, the fit between the modeled cell voltage and the experimental cell voltage. We cannot capture it everywhere completely, but in many parts of the curve, well enough to extract meaningful parameters from our measurements. Now, let's come to a very specific analysis type. This is electrochemical impedance spectroscopy, well known to characterize different processes in the battery. It can discriminate long-term processes such as the solid lithium diffusion in particles, intermediate timescales for the electrolyte diffusion, or very fast processes like the electronic charge transfer, which would happen at very high frequencies. Now, the measurement consists of an injection of a alternating current and the measurement of a corresponding voltage, which is typically phase shifted and also changes its amplitude. The results can be displayed in a Nyquist or Bode plot, and then you can get, or you can compare the model response to your measured values and try to again fit parameters. Note that this model is Nyquist, is Newman type, and there is no other assumptions. It's really physics based. We don't have any equivalent circuits. We really can adjust here the electrochemical properties of the battery. And again, we can compare different levels of fidelity. For instance, for a pure discharge of the battery with 2C, we're comparing the homogeneous model, Newman type, and the heterogeneous model, and we see both agree very well. If we do the same thing with the Nyquist plot from impedance spectroscopy, we see that for the high frequencies, both battery models give us nearly the same result, but at low frequencies we have a deviation simply because the homogeneous Newman model assumes that all particles have the same size and we don't have a real grain size distribution inside the battery. And since we have already passed 16:45 and a few minutes to go, I do not open yet another app, but you can see it here in this slide. We could import now an IES measurement, for instance, and we could select which of the parameters we want to fit. For instance, exchange current density, film resistivity, double layer capacitance, or volumetric double layer capacitance, diffusion coefficient. And if you click all 5 of them, this model solves in about 3 minutes and gives you those all those parameters out. If you select only 2 of them, the model solves much faster, but then you should have already quite good approximation or good guesses for the others, because if you set them wrong, then the model cannot obviously really match the measured curve well. All those things that I showed are available as tutorials on our website. You can build those models step by step, or if you don't want to build the models by yourself, you can simply practice by using the apps and extracting meaningful data for your impedance spectroscopy. Now let's talk quickly about some secondary effects in the battery, like the formation of a solid electrolyte interface. This is a very thin layer, only 100 nanometers thick, on top of the porous grains on the negative electrode, typically, or for instance, the graphite electrode. And it's like a skin of an apple on top of the grain. But this thin layer can really influence the battery behavior, as we all know. For instance, we are losing, of course, lithium by this process, but also the increase of resistance can be harmful, or we can have reduced electrolyte pore volume fraction. So in most cases, it's an undesired effect. And we can model this along with also other aging processes. For instance, plating. Lithium plating is another process that we typically don't want. For those of you, for whom this isn't a problem, I briefly explain. On our negative electrode, we have one reaction that is the main, that's number one here. This is what we want to have. Lithium or a C6 plus lithium plus an electron forms LeC6. This is the electric process that we want to see, the electrochemical process, but we also have a reaction of lithium ions with electrons to form solid lithium. And if we want to account for this reaction, we would simply add another porous electrode reaction. And if you have several of such reactions and you have the kinetics for it, you can just click on the negative electrode and add more such reactions. The same thing for the SEI formation. Yeah, typically literature gives some information about the kinetics. We also have tutorials on that. And then you can gradually make your battery model more sophisticated by including those unwanted effects. Let us come finally, before we enter the Q&A session, to thermal management of batteries. As we know, the thermal management of batteries is today one of the key aspects and challenges, for instance, in electromobility and other high power applications. Thermal processes do not only affect the efficiency of the reactions that are taking place, but they also affect the degradation processes that I just mentioned, plating and SEI formation. And sometimes they can even pose extreme security risks. You want to understand if your battery is likely to have a thermal runaway at some point, for instance. So it is important to assess the production of heat and the cooling needs of batteries to identify hotspots, and also to think about what happens at very low temperatures. We all know, not lithium ion, but also my car battery can respond really ugly to temperatures of minus 30 degrees if I don't take care of it. So what can we do here? Yeah, we can basically simulate the 3D thermal or temperature distribution in batteries. The processes that we can model are heat conduction, heat convection, for instance, in cooling channels inside between the plates, or also passive cooling, free convection around our cell pack if we want. Now, how is it done precisely? And here we are talking again about some level of approximation. It is of course possible to really simulate the electrochemistry and the heat transfer at the same length scale in the cell or across the electrochemical cell, which is only a few, as we learned, 100 micrometers thick. But if we know that the battery itself has thermal gradients of a few Kelvin per meter, or maximum a few tenths of Kelvin per meter, we can assume that across the cell itself, we have isothermal conditions. And that's why, to make our life easy and our computations fast, we are also able to take averaging operators to extract, for instance, from our cell model, the average heat production, and feed that into a 3D thermal model. And then we calculate the average temperature in the battery cells, and we feed that back to a cell model. Yeah, you don't have to take that step, but you will be excited to do that because it's so much faster. So this is the typical way actually of solving large-scale thermal management of lithium-ion battery packs to take the averaging functions over the volume. And what kind of heat sources can we include here? We first of all think about ohmic heating, potential losses due to ion and electron conduction, but we also have other contributions, for instance, from irreversible potential losses, entropy changes, or heat of mixing due to concentration gradients. And all of that is embedded in the terms that we offer to be activated or neglected, if you want. Now, maybe last but not least, show this thermal application here. I go to the lithium-ion batteries, and here you find, for instance, the spirally wound battery or the no, here thermal management. It's in here, 2D or axial symmetry. If you open this interface now or the model, you will detect that we have a 1D component with the lithium chemistry that is happening in 1D, and in component number 2, we have the 3-dimensional battery model with laminar flow in the surrounding, where we have a forced convection and then heat transfer in solids and fluids solved here. And if you look closer, you identify heat source, and the heat source in the battery is defined by this QH. That is the heat production, the average heat production from, defined as a variable, the average heat production from the 1D model. So this just tells us in COMSOL you can easily couple models of different dimensions with each other and get the best out of two worlds, make your computations fast, but still accurate and meaningful. Yes, with this, I'm at the end of my talk this afternoon. I can recommend you some further reading. Look into the tutorials from our battery design module, or there are a couple of very nice features that came up last month with our new release, COMSOL 6.0. And if you want to learn more, you can always contact us for a trial version of our software. We also help you to set up your first models to get you started. And if you want to learn from our development team and battery specialists, which I admit I'm not, because I'm I would characterize myself as an enthusiastic all-round physicist, but I'm not a chemical engineer or electrochemical engineer. If you want to learn from my colleagues, please join us for the COMSOL Day Batteries and Fuel Cells on Thursday, March 24th. It's still some time to go, but there you can learn from our best specialists everything in more detail. Thank you very much, and yeah, thank you very much for your attendance, and I hope you have a couple of interesting questions for me.
Yeah, thank you very much, Sven Friedl. It was very interesting in my point of view, and I'm quite sure that this created some questions from the audience. Yeah, if not, maybe I start with an icebreaker. I hope that helps to create some questions. And just when I saw, so first of all, I'm happy that there are still tests needed, you know, otherwise I would not be so happy here. Meanwhile, I see George Gramsci, so maybe please turn your microphone, your camera on, and tell what's your question.
Hello.
Hello.
Very nice overview about what is possible with COMSOL. I have one or two questions about the fitting that you showed, or the optimization algorithm that is something like an application that you offer there. I mean, there are many parameters now in a battery, and you have chosen now these 5, 6, or how many did you have there?
I think 5, 6.
At some point, if you take more than 5, 6, it's gonna be complicated now, because they are somehow correlated and have the same effect. Have you chosen the parameters with some knowing that they are uncorrelated, or how does this work?
I think this model was built before we had our new uncertainty quantification module, because this new product would allow you to really learn something about the correlation of your parameters and make sure that you you select some that really give you distinct information and not push the model in the same direction. I mean, what you mentioned is very important. I think in this model that I mentioned, the parameter choice was done based on empirical knowledge, or I would say maybe even testing. We have a number of optimization algorithms, and for simple cases, you could still also make a parametric sweep in at least a coarse grid through your parameter space to identify if you have somewhere a global minimum, which would be desired for an optimization algorithm, right? But now today we can use the uncertainty quantification module to really detect the correlation between our choice of parameters.
Okay, so there's some ways to test essentially how valid is the result, the optimization result that you obtain. So this is my concern, that basically it goes to some minimum, some local minimum, and there are thousands of them, and this is not the global minimum.
Yeah, that of course can happen. If you have many parameters, what do we recommend here? We recommend to either scan your parameter space beforehand roughly, so that you can already limit the range of your parameters to some sort of known, and only let the algorithm go the last mile, so to say, into the minimum. Another option could be to let the program deliver you the confidence interval, the confidence intervals, which is possible for some optimization solvers. And last but not least, if you have really big parameter space and you want to go for something that we don't offer at the moment, for instance, genetic algorithms or things like that, to detect even the local minima or get out of the local minima, then you can use our lifelink for MATLAB, for instance, where you write your own algorithm that jumps around the parameter space and makes sure that you're not stuck in a local minimum.
Okay, interesting.
Okay. We are very deep in the discussion already, but I would like to give another person the chance to have a question. Michael Bayer, can you please also shortly tell what's your question?
Yeah, that's. I'm always happy to see that the COMSOL guys are making my life easier, but unfortunately they're not making my life easier, because I do nickel metal chloride batteries. And so it was very interesting that when you implement the Newman model, you have an extra dimension. Is it possible for me, as I came so far with the COMSOL basic module, to implement the extra dimension as well, or do I need a module?
I think the possibility for extra dimensions is available low level for the experienced user. Maybe we can have a personal chat afterwards. I could show you where that is.
Great.
But I mean, you have worked with our tool for a while. You have done equation-based things a lot, but the average user, especially industrial user, would not take the time to really implement all those details by themselves. It is much more convenient to use the battery design module.
Yeah.
For the batteries that we support, I understand we don't support your your special type yet.
If I did lithium ion, I would use your module, but I do not. but so I have to. But the last solution is that I do need that extra dimension, and so maybe we should have a talk about maybe by email, and I contact you with the question.
Yeah.
Well,
yeah, it's possible, but it's not straightforward. It's difficult because this is really low-level functionality.
Okay, thank you.
Yeah, good. Are there other inputs from the audience? At the moment, I don't see anybody raising the hand. Otherwise, I think it's time that we could slowly. It's after already 5:04, so I think it's time that we can close the webinar. From my point of view, it was very interesting, and yeah, I would like still to make advertisement for March 1st, the next webinar, which will be from bscience.net, also very interesting, regarding the search of papers and patents in the field of batteries, especially solid state batteries. And I hope to see you next there. And thanks again a lot to COMSOL and Sven Friedl for this interesting insights.
Thank you for iBAT. You're a great community. We're looking forward to see more of you.